Welcome to Earth Science, the very first lecture of a series we'll have throughout this semester. One of the first things I'd like to do is to acclimate you to what you will be learning, talk about the scientific method, what that means, why it's so important to any field of scientific study, and then we'll get started with our lecture content for the semester on geology, which is geologic principles. So just taking a look at this image, this is off the west coast of North America, and you see a series of sea stacks. As a geologist, I have a pretty good clue and background in understanding how these are formed, why they exist in certain places and not in others. But I'm not alone in that knowledge. There are scientists across the globe, regardless of language, who can interpret the sea stacks being formed by weathering, erosion, something specifically called differential weathering, the type of rock that they're made of, because they've been trained in a similar way using similar standards. And that's part of what I want to discuss today, is the importance of science, the importance of science data, why you should care about information that you read, information that you use in your academic studies, to be sure it's good, meaning ethical, that it's sound, that it's not skewed. So in earth science, it's important to point out that you're looking at learning about a holistic set of scientific disciplines. Earth science is not just about rocks. Well, that's a part of it and an important part of geology. It's certainly not the only thing that is important to take away from the course. So before I go through these different disciplines, I want to kind of give you big picture of what I'm wanting you to take away from the course. Sure, for each smaller section that we cover, you're going to have some specific information that you'll forget probably right after you take a lecture quiz or an exam. But the things I want you to leave with should be items that should affect your long-term life as a human being and a resident of planet Earth in our solar system and universe. Those are the things that I think are important. And each one of these disciplines of science, whether it be geology, astronomy, oceanography, meteorology, yes, climatology, and even sustainability, they all work together to help us understand as humans our place on the planet and in the universe, and how we can sustain living here long term. So technically, I'm a geologist. Probably more accurately, I'm an earth scientist. Yes, I study rocks, fossils, and minerals. I study landscapes. I study the way that geologic disasters impact humans, but I also have experience and knowledge in the other fields of earth science. But geology, to most people, just is rocks and fossils and minerals. In fact, the very first thing I hear from people out that I meet or that have something they want to identify, they'll say, hey, I need you to look at this. And usually it's something like an arrowhead, or it's a fossil somebody thinks is a dinosaur bone, or maybe it's a dinosaur egg. Not always, but typically that's what they are, sometimes meteorites. All of these things are really cool, but they're very rare. And the one that kind of makes me chuckle is the arrowheads, because they're like, well, you're a geologist. Well, that's actually archaeology, that someone in the past has used a geologic material to make something that we have found in present day. So all of these things are interrelated. The geology was one part of earth science. Cool photo, right? This was right out of my hotel room at the Palazzo in Las Vegas. So this is the sphere. If you've not heard of the sphere, it is absolutely awesome. I've been there. I've actually seen the postcard from Earth, and it was really an awesome video and experience. That looks pretty real, doesn't it? I'm going to use that correlation to sometimes data that we look at for science looks very real when indeed it's not. It's been skewed or it's maybe artificial. Regardless, the sphere is really cool. So let's talk about astronomy because to many people, that's a very favorite topic that they learn about in our science. We know quite a bit about outer space. We put satellites in outer space for decades now. We've done exploration in outer space, and it will probably be the future of human habitation, of exploration of where can we live that we can survive besides planet Earth. There's a number of reasons why we may outgrow the planet with population, not having the natural resources we need, sustainability reasons, climate change, all of these factors. But astronomy has so many different aspects, and we're going to look at our solar system. That includes our sun, that includes our very own closest neighbor, which is the moon that orbits around planet Earth. We're going to look at celestial bodies, not just in our solar systems or the outer reaches, but beyond there. We're going to talk about some important astronomical events that shape what we know that happens in the universe that creates other solar systems, suns, planets, so forth, much like what happened with our own, as well as some celestial events and space events that happen right to us. Depending on the semester you take this, there could be a really cool astronomical event, such as an eclipse, for example. And then we're going to take a look at science exploration in space. Oceanography is truly the last frontier of our scientific world. While it's right here on planet Earth, a majority of the Earth's surface currently is covered with oceans, making it very challenging to explore the vast ocean floor because we can't literally drain the water out. Plus, there's life there, and we have to sustain the life. Quite frankly, we need to keep the ocean currents flowing, moving. We need our tides and waves to do their thing. All of these are interconnected with meteorology that help regulate our climate. So as a little precursor, teaser, if we didn't have a functional ocean that absorbed a majority of the carbon that's excess in our atmosphere, we'd be a runaway planet like Venus in terms of our atmosphere. The ocean serves as the greatest carbon sink on the planet in terms of absorbing that carbon and doing something with it, which is to make rock, known as something like limestone. So in our oceanography section of the course, we'll look at the ocean floor. We'll talk about the features that are down there. It's not just all an abyssal plain. There's some rather remarkable items of interest and topography, I might add. And after World War II, a vast knowledge advancement happened in the bottom of the ocean floor, including post-World War II, finding kind of the smoking guns to understanding that we do have an Earth that's constantly changing, that continental drift is real, plate tectonics is happening before our eyes. We learned a bunch of that as a consequence of World War II. We're also going to take a look at the resources that are predominantly made in the ocean, which includes fossil fuels. I have a strong feeling that most people don't really understand where and why we have certain fossil fuels in high concentrations, and I'd like you to know that it's linked to oceanography. Then we're going to take a look at your tides, your waves, erosion that happens along coastlines, and then coastal shoreline features. And I think those are extraordinarily important. A number of people across the world live in coastal regions, and you should be familiar with what these features are, not just because if you move there, they're cool, but in case you visit and ever see them. We're going to take a look at meteorology. Look at that storm. Wow, that was an impressive supercell that happened in the Waco, Texas area. In fact, I can tell you the actual date because it impacted a property that I was associated with, and we had to go out there and take a look at the damage the tornadoes did to it. And this was the residual of that thunderstorm that actually moved east. So we'll be looking at air masses, air pressure systems that can cause something like this. That can also cause fair weather systems. Weather forecasting, which is not as simple as it may sound, but the advancement in weather forecasting has been phenomenal over the past few decades. And then weather disasters and linking in that with climate change. I want to examine climate change in a way that you're given facts that are based in science and approved by an agency that is international, an organization that vets this data. So you understand what climate change really entails instead of the terms that you might hear in conjunction with policies or just general consensus of what I would call human nature. We are going to look at sustainability because I feel as a steward of the resources that we have on Earth, you need to be well informed on what you can do to be mindful of our planet's resources, the places you visit like national parks, to know what you can and can't do there, to know what is recyclable, what's not recyclable, how you can reduce the amount of waste that you generate, and then take a look at your own ecological footprint to see how you can improve. So let's move on into the scientific method. And it is the scientific method. It's not just scientific method, it's the scientific method. What is this thing you hear about and why is it so important to science? So I'm going to give an example from my dad. My dad was a surgeon. So he was a general surgeon. Let's say you had an acute appendicitis, or maybe you had a gallbladder that needed to be taken out on an emergency basis. He would have been your guy. Let's say that you had to have this surgery and you didn't get to have it laparoscopically. You probably would be in the hospital for a while. Maybe you had some complications at your surgical site. Maybe you got an infection. My dad would have looked at science data to help drive his decisions to treat you, to make sure that he could do every life-saving possible thing to keep you on the planet breathing in a healthy manner. Some of that would be blood work. Some of that would be your vital signs. Some of that would actually be looking at his patients and seeing if something was wrong. So I grew up back in the day when we could still make rounds with my dad. I could sit outside the door of a room. We're talking, this was 50 years ago. That should kind of give you a clue as to my age. And as a child, we would go there and we would just hang out and wait for him either in the doctor's lounge or literally going down the hall with him. And I do remember him talking to nurses, talking to the patients, especially if something seemed off. He would always look at somebody's record, meaning their medical chart, and he would assess all of these pieces of information together to formulate a hypothesis or a working theory about how he needed to help these patients. Sometimes the data in the chart was not accurate. Let me give you an example. Maybe they got the wrong medication prescribed or given to them, or the wrong dosage. Or maybe just a letter was transposed in his instructions about a certain type of thing that needed to be done that could change what happened to the patient. So precision was very, very important, and that links to the scientific method. So every scientific discipline, not just the field of medicine, but all scientific disciplines rely on research-driven data. Research doesn't just have to happen in some formal laboratory or with people that have PhDs or medical degrees. They happen with people just like you, undergraduate researchers. We have undergraduate research, so students can experience what that's like. The point is, you got to collect data. and you've got to collect it in such a way that it can be reproduced by other people after you doing the same set of methodologies. So let's say my dad had to go out on a trip or he got sick and there were still patients in the hospital. There had to be a doctor on call that could come right behind him and read his notes, read all the nurses' notes, and be able to care for these patients. That's kind of scientific method with meaning where scientists can pick up and follow another person's steps. With that in mind, I want you to look at the image here. This is a PhD guy with the hat on, overseeing some of my students on field course years and years ago, doing a vetted dig for vertebrate fossils of Triassic age. He had approval. Matter of fact, we had to get approval from the landowners to be there. And all the findings went to his collection that were used by Mesa Lands Community College in New Mexico for research on Triassic, late Triassic aged rock layers. So he was a renowned scientist, probably one of less than 20 across the world that are considered just the most knowledgeable people about Triassic aged fossils that exist in terms of vertebrate aged fossils. And so that was his expertise, and he had a number of research endeavors going on. So he was helping other people learn how to conduct research in such a way that it was scientifically sound through the scientific method. That's him again in the lab. The same students are experiencing undergraduate research at a place where it's really not a large place. We're talking Tucumcari, New Mexico. It's a tiny town off of I-40, off of the old Route 66, but it's still very viable and awesome research. So it could be a huge institution of research or a tiny little place. As long as research is done using the scientific method and the steps associated with the scientific method, and it's reproducible by other people, meaning people can follow your steps to test it again, then you're exercising good science. Part of scientific method is diving into the scientific literature to determine what prior work has been done on the topic that you're doing. So let's say you choose a topic that has never been studied by someone. That is considered novel research. It does happen, but usually something related to that topic's already been done and you're taking the next step. That's part of science, is scientists are supposed to say in their research, well, this is the next logical step in study after their project concludes or their literature is published, so people can continue the effort in the pool of wealth of knowledge of science for new findings to take place. So the truth of the matter is that I can't tell you that what we know today is going to be the same that scientists believe in 30 years, maybe even 10 years. Let me give you an example. So my grandmother was born in 1898. And of course, she's been dead for almost 40 years now, but I can remember digging through her attic after she passed away to help my mom and dad pack up her stuff. And she was a teacher. So she was a teacher back in the 19 teens, literally, in early 1920s, long before we had maps of the ocean floor that showed the mid-Atlantic ridge. And I remember thinking that was so strange because I grew up with those maps readily available. And I asked my mom, I said, there's something wrong with these maps. And she just kind of laughed and said, well, think about the time that it was made, the time that it was published. We didn't have that wealth of knowledge back then. So just to kind of preface this, not only my dad was a scientist, so was my mom. But I never forgot that little teaching moment that my mom gave me, because it reminded me that the maps we have now, or the data that we consider real, valid, and true today, may not be in the foreseeable future with what we know. I'll give you another example. When I was going through college, email appeared for the first time. widely used by people. It was a big deal to get an email address. When I was growing up, there was no such thing as an email. There was no such thing as a cell phone when I was a kid. It wasn't until I was probably 10 that my dad got the first big giant cell phone bag because he was a doctor and they cost a fortune. Every call cost a fortune. And we had to use payphones to call people. So you always had to have change with you to make these calls, things that aren't the same today. Who would have guessed back in the 70s that we would have smartphones that would do anything and everything for you in the way that artificial intelligence works? That's my point about understanding how rapidly things change with technology and scientific knowledge. Speaking of things like artificial intelligence, there's a place for that in science. There's also a place to recognize when humans or something like AI are producing fictitious, skewed, or incorrect data. You're not going to necessarily be the expert on something that you're researching, but you also can't take it as it's the fundamental accepted theory by scientists across the world. So I'm going to use climate change as an example. There is an organization compiled of people who are experts across the globe, which are also check and balanced by people who make policy, who are governmental officials and other folks like them. And they're all from people across literally agreeing countries to participate in understanding how our climate is impacting the planet, to hopefully make policy changes at different countries' levels to help us be able to live here and thrive long term. Data is reviewed by panels of experts to determine, is this worthy to include in the scope of knowledge that we think is accurate and true at this time for climate science? And it's reviewed on an annual basis. So there's a constant process of vetting of materials, and some stuff isn't vetted. Some stuff is like, not so sure about how this was collected, or it can't be reproduced. It didn't follow the scientific method. So vetting data is super important. So is ethically using data. Let me give you a great example. First, let me tell you what you're looking at here. This is the Cretaceous Paleogene layer. If you were to look in literature, it might be referred to as the Cretaceous Tertiary, or the KT boundary. This geologic timescale got redone by the International Commission on Stratigraphy, and it's now what was used to be the Tertiary is split into two different geologic periods of the Cenozoic era. Probably more than you wanted to know, but it's important if you were to look at data. Notice the white stripe right here. That is a layer of a rare earth element known as iridium. Iridium is predominantly found in meteorites. Oh, well, that means that this layer must have come from meteorites. That's a pretty good hypothesis. But what are the other potential sources of iridium on planet Earth? Volcanism produces iridium that comes from inside the earth, from places where we have magma forming, but it doesn't come out in the concentrations. We find it in the KPG boundary that you see right here. Super important to at least examine all possible conclusions that could be necessary in formulating a hypothesis, or when you're using data to explore the potential other sources that could contradict your findings. That's quality, sound science. So it's important that if you don't see that in stuff that you're reading, it's probably skewed and could use a really healthy dose of the scientific method applied to it. Sometimes data can be masked so well that it's easy to find a way to make it fit the scenario. So you could take your temperature 15 times. The first time you take it, you put ice cubes in your mouth. The second time you take it, you do it normal, about a half an hour later, like It's just a true finding of what your real temperature is. An hour later, you decide, hey, I think I'm going to take that and I'm going to put it under the heater. You've just skewed data, right? So we have to understand how data was collected and make sure that it's done in a scientifically sound manner. So that was kind of a silly example, but the silliness is important because sometimes it doesn't look so silly when you're looking at published data or people that have really good credentials, and we just make some assumptions that they're accurate and true. The scientific method is important to geology and our science for this reason. Not just all the reasons I listed, but because we've generated theories and principles that scientists operate regardless of where they are in the world. And this is an example of that. This is the island of Hawaii, the actual big island. And it's an active lava flow. I got to shoot from a helicopter with the doors off. That was a cool adventure. And then I watched it drain into the ocean in the upper right-hand picture, creating a hydrovolcanic eruption, which in turn super cooled the lava and created this stuff that makes up black sand beaches. Way awesome, right? But we can tell you as scientists that these principles apply regardless of where this process happens on the planet. Since Hawaii is a case study in continental drift, scientists across the globe have studied it extensively and done research and built one piece after another of sequential research that supports the evidence that Alfred Wegener suggested, that the Earth's plates were constantly in motion. That means that with the scientific method, we need to see how it applies to the work that you'll do in this class. You're going to have a number of labs that you do that I ask you to formulate a hypothesis. I've learned that that is a scary thing for most students. And I can remember doing my first one. It kind of was for me too. But you'll get better the more you do it. So here's a photo I took going to Arizona over the Grand Canyon in an airplane. And I want you to notice that this is important. These rock layers way down here where the river is, and then the layers right above them. So much study has been done on these rock layers that we know that the oldest rock layers of the Grand Canyon are at the bottom and the youngest are at the top. While that may seem obvious, it's so obvious now because it's been supported with all this research that we have a principle that supplies geologists across the world with an assumption known as a geologic principle called the law of superposition, which I'll get to in just a second. But good scientific work is based on the scientific method where a person formulates a hypothesis, they research the literature to look for prior work done on it, to support the guide, basically a beacon in the direction that you're headed, to evaluate that information. They conduct their research, they share their findings. And in this case, we would need to get out there to conduct research, get approval from the National Park Service to actually go do this research in the Grand Canyon, especially if we're collecting something, because you can't just take stuff out of a national park. You can't damage rocks. And then we need to analyze and share that information with what we learn. So the scientific method has helped us formulate geologic principles that all geologists around the globe use. And I like to share this story because it's one that I have never forgotten, kind of like that teaching moment that my mom gave me about the maps of my grandmother's. I was on a plane coming back from Hawaii. I'd just been to this remarkable course for geology teachers, just like what I do, professors. And it was taught by a geology professor, which was pretty cool. And I had all these photos and I cut through those. I was labeling them, kind of getting my digital library in order. And I was going through field course pictures of places like Sedona that you see here and Zion National Park. Now, most of the flights in Hawaii coming back to the States that I've been on occur in the late afternoon and you kind of spend the night on the plane. So imagine that it's after midnight. I was sandwiched between two people. I got the economy seat, right, for a cheap flight. And so there was somebody from a different country sitting next to me that spoke Chinese. And then there was somebody who I didn't talk to at all, sleeping on the other side of me. And I'm looking at pictures of cross bedding from Zion, just these extraordinary photos of the Navajo sandstone. And this man, I mean, woke people up by going, whoa, he was so excited. He knew what I was looking at. He had been there. He had studied it. At first, I'm thinking, what is wrong with this guy? Well, it turns out he was a petroleum geologist. He worked in China. And the way he communicated that to me, because he really wasn't fluent in English, I certainly wasn't fluent in Chinese, but he grabbed one of those little bags that you can use if you're sick, and he started drawing rock symbols. And that was eye-opening for me, because through the common language of geology, through principles that we both shared, that we had both learned regardless of where we took our geology background courses, we shared a common knowledge and language. So these geologic principles I'm fixing to share with you do that. It doesn't matter where in the world you are, they're still interpreted the same way. Probably the most fundamental one is the law of superposition. And I mentioned this earlier. The oldest rock layers are at the bottom. I use that as the scientific method example if we were going to go do a study. So older rock layers are deposited before younger ones are. The key thing is deposited. That means made. So rocks can get shuffled out of order. You're like, that sounds weird. Rock layers, that is, because of faults that shift rock layers, or maybe we have erosion of some rock layers and new rocks put on top of it. So there's some reasons why this is important, because we know, let's say if you look at the science building on campus, there are actually 5 stories in the MCC science building. There are 2 basement floors. The first floor that people walk in, which is the ground floor. Floor 2, which is where the geology room is, and floor 3. But there are really 5 floors. So we couldn't have put the ground floor on before we built the second floor in, right? But I certainly couldn't have put floors 2 and 3 on without building floor 1. So floor 1 is older than floor 2. Floor 2 is older than floor 3. That's how the law of superposition works in geology. The law of original horizontality is important because rock layers are typically laid down in a flat manner. Just the law of gravity causes that to happen. But sometimes rock layers can get bent, which is called folding, or they can get uplifted. Look at this remarkable rock outcrop right outside of Estes Park near Rocky Mountain National Park in Colorado. That is called vertical folding. It's extraordinary. So that's mountain building that created these rock layers to get pushed up. The rock layers were already in existence. They were already like this, flat, and then they got smushed up. That doesn't happen by itself. Actions happen. The point of this principle is the rocks were originally laid down flat, and then later on they can be deformed or tilted like you see here. The law of lateral continuity is one that is important because anytime you see canyons, this is a great example of that. Canyon layers extend in all directions until they pinch out. Or if you're lucky, you can see both canyon walls like you do right here on the east side of Zion National Park in Utah. Where I have the yellow arrows, those rock layers should merge, but we've had erosion and weathering, 2 very different actions I might add. But nevertheless, there should be rock there and it's missing, and it should be the same rock. So if you look at the diagram on the left, the layers 3 and 4 have been carved out by some weathering and erosion agent. That's what's happened right there in Zion National Park. Grand Canyon's a great example. So I'll give you another way that this principle is used, or law. By the way, we refer to them as laws and principle because that's what they are in general layman's terms. When I was earning a Girl Scout badge years ago, I had a cooking badge I had to get. And so my mom was an excellent cook. So she was also my Scout troop leader. And she wanted me to earn my stuff fair, square, and ethically. That's the scientist in her, right? And so she took me to the store. I had to buy all the ingredients, and then I got to make my favorite cake, which was a double chocolate fudge cake. She didn't let me ask her for help. In fact, she said, it's all on you. You got to choose the pan. You got to choose how you make all the stuff. I'm only here to make sure you don't burn the house down, because I could have. That was my first cooking endeavor. So I chose the biggest, baddest, largest pan I could find to bake a cake. And it was way too big for the one cake mix that I had chosen. She didn't say a word. So when I filled that pan, I'm putting the batter in, it only filled the middle of it. And then it started to spread out by gravity, but it never reached the edges of that pan. That's an example of pinching out. So rock layers do that. The closer you are to something like where the batter is, which I would use as a mountain range in real life scenario, the thinner those rock layers get until there's no more evidence of it. So that's also the law of lateral continuity. So they serve a purpose in either way. This principle or law, it helps geologists understand how to map out and why certain rock layers don't extend across the globe. Moving on to the law of cross-cutting relationships. This is an easy one to understand. So rock layers don't get crossed over by older stuff. It's going back to that law of superposition, using the science building as the ground floor, second floor, third floor. If we got a crack in the wall in the building, I'm not saying there is, but I'm saying if we got a crack, that would be a cross-cutting relationship. The crack happened after the building was made. So that's a great example. So let's apply that crack to a geologic fault or a dike. This is a dike. It's an igneous intrusion. If you see where I have this is right along the Grand Canyon. That would be like this 4. So if we had layers 1, 2, and 3, let's just say this is layers 1, 2, and 3 right here. And then we got layer 4 that came up right here. And then this is layer 5 and above. So obviously 5 is younger than the dike, but the dike is younger than layers 1, 2, and 3. So anything that crosses over a rock layer by definition must be younger than the layer in which it crosses. Just has to be. The law of inclusions is one where people sometimes don't quite get the first go round. So let me make it pretty simple for you. This law states that if you have inclusions from older rocks, by definition, those inclusions must be older than the rock itself. This was one of the coolest inclusion rocks I've ever seen in Acadia. It was on one of the beaches there. It was huge. I loved it. It was so awesome. These gray pieces are the original rock pieces, and then the lighter colored material is granite that actually came up in the Acadia area and melted some of the rock layer, but not the whole thing. That would be an example of the law of inclusions. So if you find an inclusion like a piece of conglomerate, that kind of rock, the pieces that make up the conglomerate are older than the conglomerate itself. They have to be by definition. So that's a fairly straightforward way to understand inclusions. The law of faunal succession is used for relative dating of rock layers, and in some cases we can absolute date some fossils, but essentially we're using fossils to help us narrow the scope of how old something can be. For example, if I had this trilobite right here, I'm not going to find trilobites in the same layers where the first hominoid species or human fossils are found. Impossible, because trilobites clearly went extinct based on data and research that was done globally using the scientific method. We know that they pretty much went belly up extinct at the end of the Permian period. Likewise, I'm not going to find trilobites hanging out in rock layers with these guys right here, dinosaurs, or with mammoths. Impossible, because they were extinct long before these organisms came into play. Same thing would be true with finding non-avian dinosaur fossils with hominoid fossils. Haven't found them yet. So let's say that does happen in the future. That would redefine not only the geologic timescale, but a lot of theories about the sequential order of fossils in the fossil record. But the law of faunal succession kind of puts things in sequential order based on the fossils that we find in those rocks. The last of the laws and principles that we use in geology is something called the law of uniformitarianism. That was a concept really developed by the father of modern geology known as James Hutton. His phrase was, "The present is the key to the past." So let me show you the coral reef that you see of Elkhorn coral. Elkhorn coral pretty much survives in 1 atmosphere of depth of water. If you're a diver, you know what that means. I'm certainly not going to be in 40, 50 feet of water. It's just too much pressure, but you could probably find it in 20, maybe 30 feet of water because it needs not a lot of pressure on it or break those beautiful arms that you see of corals. So let's say I find coral fossils from something like this in rock layers like this in limestone. Then I could hypothesize that the depositional environment that created those rocks that had the same fossils in them has to be about the same depth that we know that Elkhorn coral lives today. So that is what the present to the past means. So that long word, uniformitarianism, simply means this. James Hutton believed that things were fairly uniform in terms of geologic processes on the planet, and occasionally we'd have a hiccup. If you want to call that hiccup, a natural disaster would be a good example. But things uniformly are happening over geologic time. So when you kind of break that apart, it makes better sense. Things operated in a similar manner throughout most of geologic time. In conclusion, I want you to think about the principles you learned about today. Contemplate what they mean, be able to apply images that I might put to say, hey, what geologic principle would apply here based on your knowledge that you've been given. Think about the data that you're going to use in your labs this semester. Always give a second thought to, I wonder if they use the scientific method to get that information, and do a little bit of digging and don't just rely on what I would call the internet search, especially just relying on Wikipedia. It can be very good, but not all Wikipedia entries are accurate. That's a good example of anybody can add to the pool of learning. It was a great endeavor to try to get information out there, but just because it's there doesn't mean it's accurate. And I would say the same for printed materials. Your job is to start deciphering what is good science and what's not in this course. As we journey through our science, I just want to welcome you to this exciting world that we have of geology, astronomy, oceanography, meteorology, climatology, and even sustainability. And I hope that by the end of the semester, your perspective and your lens by which you see the world has shifted a bit with a little bit more knowledge and discretion on how you see the scientific materials that you look at and the places that you visit. I welcome you to the course and say thank you for being a part of it. Bye.